We've been learning about light, and we saw in our last lesson that light can behave like a wave, that it's made of oscillating electric and magnetic forces that push charged particles around. Here's the thing though, in the early 1900s, there was an experiment done called the photoelectric effect. And it turned out that we couldn't understand its results without thinking about light as a particle, which is really strange. This is actually a suggestion of Einstein, and he said the best way to make sense of the results we see in this experiment is that light sometimes behaves like a particle, and light sometimes behaves like a wave. Strange stuff. Let's see if we can figure this out. So what's the photoelectric effect? Well, basically, as you can see in this experimental schematic below, if you put light down on a piece of metal, so you shoot light at metal, if that light has the right characteristics, it will pop electrons off. And here it is shown going up to this energy analyzer. And basically all that does is it tells us how fast our electrons are going. So there's two things to keep in mind when we're doing the photoelectric effect. What's that light like that we're putting down on it? And how much energy do those electrons have that are coming off? And the reason this experiment was so important was because if light was a wave, we should get some very particular results in this setup. And we actually got very different results. And so what I'm going to do now is talk about what we expected and then what we actually saw. So what do we expect to see? Well, if light is an oscillating electric field, what that means is if we make light brighter, no matter what color it is, the electric field gets stronger. And so what we'd expect is if you're trying to pull a charged particle, an electron off with an electric field, all you got to do is get a strong enough electric field. All you have to do is make your light bright enough. So one thing we expected was that any color of light, if it was bright enough, if the electric field was strong enough, could eject electrons. So any color of light, the wavelength and frequency don't matter. All that matters is how strong that electric field is, how bright that light is. The second thing we expect is as you make that light brighter, you get higher and higher energy electrons. So basically, you put in more energy with that light, you have a stronger electric field, you're going to accelerate that electron more. In fact, neither of these things were observed. So both of those turn out to be wrong. We didn't see them, and yet we'd expect that if light was just a wave. What we actually saw is that electrons are only ejected by some colors. So it turns out that not all colors will eject electrons. You have to get far enough towards the blue side of the spectrum, what we know to be the higher energy side of the spectrum, before electrons start popping off. The second thing we saw is that brighter light didn't lead to higher energy electrons. Instead, it just led to more electrons. So those electrons were the same energy. They were moving the same speed when they came off, but there were more of them when we made it light brighter. Not what we'd expect if light was just a wave. The final thing is if we want to increase the energy of those electrons, we don't change brightness, we change frequency. So higher frequency light did give us higher energy electrons. So when that experiment was first done in the late 1800s, people didn't understand it. And it wasn't until Einstein proposed a solution in the early 1900s that we actually figured out what was going on. And he said something pretty outrageous. He said, let's not think about light as a wave, let's think about it as a packet. It's more like a BB in this case, he says. And these packets of light have an energy that's given by the frequency of the light. And that's what this expression tells us down here. This is his proposal. He says the energy in this light packets is equal to the Planck's constant, h, times the frequency of the light. So he says that the energy in our light packets is determined by frequency. And I think that will help us understand the results we saw in the photoelectric effect. So below in this graph, we see plotted some results from a photoelectric experiment. And what we have on the y-axis is the kinetic energy of the electrons in electron volts. And so basically, as you get higher and higher on this graph, you're getting electrons that are faster and faster. On the y-axis, we have frequency. So as we go from left to right, we're increasing the frequency of that light. And Einstein's proposal helps us understand this picture. What happens is when we're at lower frequencies, so over here, you see this red line is at 0. That's basically telling us when I shine light on it of lower frequencies, I don't see any electrons. They don't have any kinetic energy. And it isn't until we get to some critical amount of energy amount of some critical frequency that we start to pop off electrons. So right there, at about 10 times 10 to the 14th hertz, in this case, we start to pop off electrons. And that's why this line now rises. And it continues to rise as we increase frequency, just like we said in the last slide. As you increase frequency of our light, you get higher and higher energy electrons coming off. And so Einstein's explanation helps make sense of that. Why? Well, because if the energy of these packets coming in and striking the metal is proportional to its frequency, then if we have light with too low of frequency, it'll never pop off an electron. Because electrons are basically glued into our solid. There's all these attractive forces, the positive nuclei, holding those electrons in. And until our packet gets enough energy to launch that electron off the metal, it won't pop off. Once it does have enough energy to separate the electron from the metal, that's at these higher frequencies over here, well then the more energy that BB has that whacks that electron, the faster that electron's going to plop off. So Einstein proposed the solution. He says the only way we can understand the photoelectric effect is if we think about light as a packet. Hey, hey.